So it's a pleasure for me to welcome all of you and to open this Summer Solstice 2023. And I think that Danuta will help me telling the history of this workshop, which has quite a number of years now, and survived after the pandemic, the period in which it was suspended. But thanks to Danuta, we had a very informal meeting last year, and so we decided to start again. And so I'm quite happy to have you here and to have hopefully also also people attending from distance. So the idea, as you can have understood, is to talk, to have very informal discussions, and so please, so I suggest you to leave some time for discussion, to try to involve people to participate into the presentation. So just a few practical information. Here, this is the old building of a physics department. Now we moved very far from here, near the airport, but still there are near here, just here we have the observatory. If you walk up on the hill, you arrive just to our observatory, where there is the National Institute of Astrophysics. Here we have essentially two things that are supporting this conference. The first one is the Department of Physics. Yes, it's this here. I can explain then what is going on, but I think it is this one. Okay, and we have the GGI, it is the Galileo Galilei Institute for Theoretical Physics from ENFN, and the Department of Physics. Then I shut it up. And so in this part of the building that you can see from the window here, there are some rooms open if you need to organize a meeting or to connect. Sometimes you are involved in some reunion, so you can profit of this place. Here you have a coffee machine. We don't have coffee breaks. We have coffee breaks, but without coffee, because it is a self-made in order to save some money. And but we have lunch here. We have a cafeteria, and catering will come. And so you in the cafeteria, then maybe Giovanna. Giovanna, can you stand up a moment? Giovanna is here for help you also. Or you can also ask to all Italians here. There is a water machine. You can use your water bottle here to pick some water, and so then you can ask. Okay, so I invite the first speaker of the morning, Danuta, to present. If you want, we can present together this conference, or maybe you can introduce us in this conference, and then clearly to speak about your research. Here you see you have the program here, and you can I think it is working already. The meeting is streamed on YouTube. You can see here. So if you have collaborators and you want to share with them your talk, you can also use the link that I provided. Okay, please. This one, huh? Yeah. Okay. If you need, there is both portable microphone or this one.
Is it okay? I don't know if I need the mic.
And you need this because otherwise people in the are following. Okay. But if you are more comfortable, you can use this one.
Then I can move. Yeah, so it's my great honor and privilege to open this little conference, this little workshop, especially the conference of discrete models of complex systems. So and the talk in this Galileo Galilei Institute. So the institute, the place where the revolutionary thinking many years ago was born. And I think that my presentation on synchronization in and the network of controlled oscillatory servo automata will be also inspiring and a kind of revolutionary, provide some revolutionary thinking to you. So the frame of the frame of the system which I would like to present is a three-phase timed automata. These phases are firing, refractory, and active, and each of these phases has his own time states. Let me say. So we have F time states of firing, R time states of refractory, and A time states of activity. All of these automata are coupled by a two-dimensional stochastic network relations of nearest neighbors, and this kind of coupling results in the free evolution of each automata. Means that automata periodically increases time state, going cyclically from firing through to refractory and to active. Because of couplings, an automaton which is in phase A and it has enough neighbors in a phase F, then the phase of this automaton is reset to the first time state of phase F. So coupling basically means resetting. Basically means resetting automata in active state to the phase F. And with this simple three-phase timed automata, we could reproduce the tissue of propose to reproduce the tissue of the right atrium of the heart. So networks are ubiquitous in the nature, and especially in human, especially in biology. So neurons and the brain is the basic and the prototype network, prototype system of interacting entities. The other one are myocytes. Myocytes are cells which build the tissue of the atria, not atria, of the heart in general, and we will discuss, we will just try to mimic their properties while modeling right atrium. And this right atrium, it means that we have this is a mechanistic model, so we have a kind of frame on which the basic element is the is the sinoatrial node. It is the piece of a tissue which initiates the impulse. It produces the impulse, which then this electrical impulse propagates to the right atrium and reaches the next piece of a tissue, which is called atrioventricular node, to cause contraction of ventricles, contraction of ventricles. Okay, so going further, we interpret our automata, cyclic automata as a phase automata, automata in which we observe synchronization. And what does it mean, synchronization? It means that we have some adjustment about rhythms of oscillating objects, and there are two possibilities that we have the frequency adjustment and phase entrainment. In the frequency entrainment, to both of these kinds of synchronization, we will use famous Kuramoto parameters. The first one describes the frequency of the now let me say the histogram of frequencies, and the second one, how close are phases how close are phases of the oscillating units. Okay, so our system, thanks to the network couplings, we quickly observe subordination of the phases in the form that we observe the moving waves, propagating waves, and two forms of waves can be observed. Very short one, this fastest one, which do not have for which activity phase is very short, are the fastest one, and the other one when the total cycle, total intrinsic cycle of the automata is performed. In both of these stationary states, the frequency Kuramoto parameter equals to 1, so all of these automata has the same periodicity. However, the phases are distributed equally, let me say, and so when we sum all these phases, then the resulting value is zero. What else? Yes, just to mimic physiological observation, we wanted to model so-called vagal impact on our automata. Vagal is a part of autonomic nervous system which speeds up or slows down the heartbeats. And the vagal is especially responsible for slowing down the heart contractions, and it is done via go back, go forward. It is done because of the release of acetylcholine. If acetylcholine is released, then the next contraction will not go just after. The next contraction will be delayed for some time, depending on the acetylcholine level. And many results have been published in a famous, let me say, issue of famous journal Physica-D, an issue of this Physica-D, which were collected the materials, the papers of the Dresden conference, in SummerSolstice conference. So what we propose to consider vagal, to propose vagal activity in the mathematical form as follows. So we assume that activity, that number of steps of this time states in activity can change in time, and it is described by the VR function, and this VR and in our simulations we assumed that this VA activity is a two-level system, reconstructs two-level system. There is acetylcholine on the C1 level or on the C2 level, and it changes periodically. We perform a series of the following experiments. The whole experiment consists of 30,000 time steps. We evolved with cellular automata to reach the stationary states with the basic without any vagal interactions. Then we introduce these vagal interactions with these periodic switches from C1 to C2. And make the final statistic estimates after many time steps. So the expected period of the automata and perturb automata is t equal 50, and expected automata period when this vagal activity is constant is 75. This is given just to understand the next results. All periods of vagal activity from 4 periods. So this t VI from 4 to 200 were simulated and 100 times. So Kuramoto parameter, the results are presented by Kuramoto parameters, histogram of periods, and order parameter of phase synchronization. So our result looks like follows. So what we can see. So this is the increasing period length of this controlled system, and the resulting Kuramoto phase, the level of synchronization. And we see that this perfect synchronization occurs in a strictly restricted windows of the vagal activity. In the case, it's 52 to 74, 102 to 120, and so on and so on. This red box corresponds to the standard deviation of the obtained results. So it is noticeable that this perfect synchronization goes without any error. So it is the almost sure phenomenon. Okay, so this picture, what is the reason for the kilter? Let us see in particular for the case when the period of this vagal activity is 64. So after 3,000 time steps with the normal activity, the activity is switched to the next. The activity phase is longer by 250, and it means, and then as you can see, when this activity goes down, is switched to that, then we observe something like a step in our Kuramoto, in the Kuramoto model, in the Kuramoto parameter, and it happens that these steps occur exactly at the moment of starting the new period of the vagal activity. So in the stationary state, at the end we have, as you can see, perfect agreement. All automata go with the same phase. So thus reset is the source of synchronization. Synchronization, it was the Kuramoto. Let us present how the histogram of periods looks like. So before the switching the vagal activity, we have the expected intrinsic cellular automata period, while after we have the period of the control, not the period of the control. And so the explanation is that we have n square couplet cyclic oscillators performing a stationary evolution with some expected periodicity, and in the stationary evolution means synchronization in the waves, in the waves of excitation which wander over the network, and it means that each time state, from 1 to F to R to A, so this is the length of the intrinsic period of automata. So this each time state, they are almost likely, likely to be evenly distributed. So we have just this number of automata in the same state. So as the states are equally represented, the resulting Kuramoto parameter is zero. Then when we switch into this next level of Waggle activity, then all automata in a phase may stay longer in this phase. So we have a kind of surplus of automata in the phase A. So, and this surplus after half of the period, this surplus automata are reset to phase F. So this surplus plus the remaining automata of the ordinary revolution, all of them are in state T, the first state of the firing phase. So it results that Kuramoto order parameter increases by the size of the surplus. So these are reason for these jumps, and the automata were reset. These automata which were reset together, let me notice that they must follow the controller period, because they exactly follow this period, and this process of subordering phases repeats at each reset. So finally we land in a system synchronized with synchronized when all automata go together with the controller, with the period of control. Okay. Yeah, this is nice explanation, but it as you could see, it works only in particular windows. So in case when in case when we have the Waggle activity period equal to 50, so exactly the same as intrinsic period of our automata, we see that there is a first jump in this Kuramoto phase parameter, but then it stays on this level. It does not go up. It does not goes up anymore. So we start with a system with evolving with the period 50, and we land in the system evolving with the period of 50. In this case, we have that both periods, controller period and the automata period agrees, and two time steps longer control allows us with small steps by step to increase the Kuramoto order parameter to reach the perfect synchronization with, of course, 52 with the controlled activity, and it goes perfectly up to 74. Why? Because if we go to 76, then what we have also automata which are locally somehow involved in the ordinary with its intrinsic frequency. So we have two frequencies on the lattice on the network: the intrinsic and the controller is only 40%. So in case of 74, we have even smaller representation of this controller periodicity. Most of these results were presented on our last year meeting. When I discussed zero-phase synchronization in a network of this time automata on our in Gdańsk, it was in June, and having the occasion to revise all these results, I have found that most of the results which the model developed, the model was created, and the model developed just as the step by step, going from the first meeting in Gdańsk, in Gdańsk, when I study only sinoatrial node and think how to make the homogeneous stochastic network move the homogeneous stochastic network to the heterogeneous network to reproduce so-called leading pacemaker sites, and we proposed diffusive preferential rewiring as a motor for stochastic heterogeneity in a network. And this diffusive preferential rewiring, so we don't want to, so we don't want to be connected to the next neighbor, to the nearest neighbor, but we choose some next neighbor of him. Just reminds me our coffee breaks and social meetings, when we do not want when we do not need to talk exactly to our nearest neighbors, but we can just see what is talking about, what the next our neighbor is talking about. So here you can see some people involved in the first meeting. Then we move to the next. Another picture from this conference also. When we as I say, then we moved to Nancy. In Nancy, our meeting, our summer solstice meeting were just after automata conference. It was organized by Nazim Pates. Nazim is the main organizer in this conference, and here we moved to Turku. When I also noticed that not only me were interested in synchronization, but also about synchronization in automata. Franco have a speech, and however, so in Turku, I proposed that to improve the basic coupling rule of automata by allowing by changing, so not only resetting due to coupling with its neighbors, but also when an automata is in refractory state, it could stay longer in this refractory state for a longer time when there is enough nearest neighbors around in a firing phase. Then after this modification, we observed synchronization with periods much greater than the intrinsic period of the automata. However, nobody remembers from Turku. Nobody remembers Turku and my lecture and my proposition. But what we remember from the Turku, all of these participants, I hope that some of people remembers that it was the boat trip to the sauna, to the Finnish sauna. The nice social conference dinner organized by Jarkko Kari so it was in this really shortest night in Finland. It was extremely evident, but this picture was taken at the noon in this day. Okay, so some pictures of our sauna. Yeah, I didn't put our how above pictures I've got. However, as you can see, you can notice plenty of faces are really our faces from the present conference. I am really sorry, but I didn't attend it to the conference organized by Franco in Ardoso. So I can only put the poster of this conference. The next conference was in Warsaw, and it was organized by Andrzej Krawiecki from Technical School of Warsaw. And you can see also the other, you can see here also our main organizer, Franco, talking together with Anna and his husband, Bruno, the other co-organizers, very frequent participants of and motors of our meetings, Anna Ławniczak and Bruno Di Stefano. Okay, so maybe results are not so important now. However, the zero-phase synchronization I have found for this extra rule, in case of deterministic evolution, when the delay on the refractory phase was entered, then we also observe zero-phase synchronization. The next summer solstice was in Ljubljana, and I didn't attend it. Sorry. I hoped to meet Tatiana here, the main organizer. However, I can't see her. The next one was in Toronto, organized by Anna, conference by Anna, but due to shortage of money, I didn't go to Toronto. But the next I attended, I participated in Aveiro, Portugal. The main organizer, Professor Mendes, and we enjoy palmas in Aveiro, plenty of palmas around the university, but also wine was good to remember. And next, our system our conferences go to Catania, so we land in Italy, in Sicily, and the conference was organized by Professor Rapisarda, and we also, you can notice plenty of known faces going, standing, and walking in Catania together. It was the first conference when I put the proposition of atria, because until the Catania I study only, let me say, pacemaker, cellular automata as a pacemaker of the pacemaker of the heart. So the sinoatrial node. Then I put this sinoatrial node to the wider background, and as you can see, you can see two sinoatrial nodes. This is because I was interested in patients after heart transplantation, after heart transplant people. So they have often two pacemakers, own pacemaker and the new pacemaker, and this pacemaker cooperate or do not cooperate with each other. So I studied the problem of arrhythmia in this case, and we also enjoy the food, the food in the Sicilian food, Sicilian food. This was Sicilian special menu in the conference dinner. So the next conference was in Gdańsk. And this is also some photos of the dinner, of the conference dinner. This dinner was in town hall of Gdańsk. So you could see that some let me say like in a museum arrangement, and then there was a conference in Dresden, organized by Andreas. When I put to my model some more formal form, and however, this Dresden conference and Dresden organizer, I think, will be remembered and is remembered by me. Often listen to this Andreas band, music. And this band didn't. Yeah, it was very nice that we do not only can make nice pictures, but also can enjoy other parts of life. Okay, so now we are at the end. So the photo of our last meeting from Gdańsk. Yes, when we, let me say again, together, then the core participant of this series of conferences and the participants of this small conference in Gdańsk. So conclusions. Yeah, going back to the synchronization on a network. So we have found during this more than 10 years, of development, we found two ways to observe synchronization in couplet cellular automata. So the first one resulted from elongation of the refractory phase as the effect of couplings with the nearest neighbors. However, this result is achieved in many time steps and only on a dense network evolving deterministically, so it's not physiologically justified. And the second one was due to a periodic reset caused by external control, achieved quite quickly and efficiently. However, period of control, only in period with the control with the certain windows. And when closing, let me send the special wishes from the Cathedral of Fromborg. Yeah, just we are in the Galileo Galilei Institute when the famous Italian astronomy, and Nicolaus Copernicus. It is a famous astronomer, a Polish astronomer who learned here. Maybe not in Florence, in Padua and Bologna. However, close in the close part of this Italian. Yeah. So, thank you very much.
Thank you, Danuta. And so you see that the main goal of this workshop is to enjoy ourselves.
Yes, so the main thing is just to be together, to enjoy being together, to establish friendships and to keep this friendship. So it is really nice to see what is going on, and how life is going on, how physics. I don't know what is your background, but most of physics background.
I think that Rolf maybe is the one who has collected more presence in this workshop. So maybe Rolf, come here and say some words how you arrived in this company. In the meanwhile, I remember that Galileo lived just the last years of his life, just near here, not here actually, but not very far from here. There is the old Galileo's house. It is almost empty. They are now planning to refurbish everything and to transform it into a place where artists can come. There is a project here. Maybe tomorrow when our artists will perform, but before them, maybe I can have a presentation of this project that is going out here. Maybe Giovanna can help with to organize this. So, Rolf, how did you arrive to this conference? You stayed in almost every, except maybe Arcidosso and last year because it was very informal. So please.
Hello. Yes, actually, I am a computer scientist, and My main scientific work was on computer architecture and hardware for cellular automata. And once I noticed on the internet there will be a workshop or conference in Dant. And so I went for this workshop and presented how cellular automata can be built in hardware. So this was my first talk. And then I attended several of all the nice workshops, and there were very nice friendships also with Anna.
But you were not an organizer.
Yes,
Oh, so
I'm
we missed you.
not
Yeah,
really an
you
organizer,
should.
but I attended several times. It was very friendly atmosphere, and also from the scientific point of view, very nice influence from different parts of scientific
Yeah.
information. So it was a pleasure to join all these conferences, and thank you very much for the main organizers, for Danuta,
Yeah,
Anna,
and yeah.
and Bruno, and so on. And for Frank, of course. Thank you. Thank you.
And so now let's pass to the scientific part.
Yeah.
Are there questions, comments on Danuta's presentation? I have one in case. So clearly, this is a workshop on discrete system. But what happens? What do you think will happen if you use a continuous representation of your neuron? Because clearly, perfect synchronization.
Yeah.
For instance, in the Kuramoto model with a say linear coupling or most linear coupling is not really possible. So you may expect some dispersion at least.
Yeah, you are right. You are right that switching that living discrete times that living that discrete models, yeah, for sure change change most of that. However, however, what I wanted to and I've got some results on that. I do not, I cannot show them. So Kuramoto is very.
Just say if you expect something. So, for instance, you have tried with several states, no? I think that the minimum is 3 to have these waves, but you can have more.
Yeah.
So, did you notice that increasing the number of states that is coming nearer to the continuous case? Something is.
It's not that way. No. It's not that way. I think that it will be not that by increasing, but the role of of these particular states, because we are notice that each state has own idea and our idea what is it for. Yeah, we have the phase of this firing, which means only sending signals. These are not, so the states are not equivalent each other. And this is basic case. For physiological point of view, what we need finally, we would like to have cells or cellular of automata in the same phase, not exactly this continuous state, but rather we want them to be fired at the same moment or almost the same. Yeah, just to see that the signal moves very quickly, immediately.
And so, if you want to participate, clearly raise your hand. Another question is, I remember, I don't know if it was yours, you once, probably you, presented the case in which you have some tissue with damage that can break the uniformity of waves. This is something that happens after heart attack, that you have some.
Yeah, the points, yeah, of arithmetic. Yeah, so this is again the other, yeah, yeah. This is this part which I called, which we related with arrhythmic events, which can happen on the tissue. It is arrhythmic events. The basic source, some imperfection of the networks, of the heterogeneity of what is very important in physiological system is that the cells, the real myocytes, can be tired, we can say. So they can refuse to follow the orders of neighbors. So yeah, these are the moments when the discrete, then this discrete approach can be too simple. However, when we see so strong effects, this is like in, I think this is similarly to the phase transitions, that the details of this Ising model, how these neighbors interact with each other, how they are linked to each other, it doesn't matter. But because the general is that if temperature is enough strong or enough low, then we observe the total result, and this is what I wanted to present here.
Okay, so thank you, and if there are no other comments, I invite the next speaker to come here. This one. Where is the? Yeah, there you go. Okay. Just okay. I have to no, go. So please, Barbara, can you you can show us your results about the difference between the case of finite grids and the case of infinite grid in the context of number conservation of non-uniform cellular automata. So, okay, when we finish the title of the talk is already.
Hello to everybody. I am very happy.
Now you can use
Yes,
the micros now, but because there are people following us in streaming, so they don't hear you if you don't use the mic.
Okay, so
There is also this one if you want.
no, it's enough. Okay. So I am very happy that I could come here to Florence. Yesterday I saw a small piece of this town, but I am in love, yes. So for this opportunity, I would like to thank the organizer very, very, very much. Thank you. Okay, so I want to present some new results about number conservation of non-uniform elementary cellular automata. I investigate this topic with my colleague from Gdańsk University, Maciej Ziemiańczuk. Here, Maciej Ziemiańczuk, who is a computer scientist, but I am mathematician. Are there some mathematicians here? Please give me a sign. Okay. Okay. So again, I am mathematician. I am very sorry for that. Okay. So I discussed the case of finite grids last summer solstice in Gdańsk, and these results are published now. And today I want to discuss the case of the infinite grid, and to point out some differences between the case of the finite grids and the infinite grid. Okay. So let us start with a elementary cellular automata with the classical uniform elementary cellular automata, they are very simple. They are one-dimensional, binary with radius 1. So cells are arranged along a line, yes, and we have some binary local rule with 3 variables, so-called Wolfram rule, and a given global rule generates local rule generates global rule capital F in the usual way. In each time step, the cells update their values, and the new value of a given cell is obtained based on the current state of the cell itself and its left and right neighbors. So and all. It's all. And there are 256 elementary cellular automata. The dynamics is very diverse. But okay, in fact, there are only 88 independent elementary cellular automata because some of them are equivalent one to other with respect to these 3 simple transformations: conjugation, changing 1 to 0, 1 with 0, reflection, changing left and right, yes, and composition of them, yeah. Okay. And to accordance for conservation law, one of the most concepts in physics, usually number-conserving cellular automata are used, in which the sum of states is preserved at every update. In the binary case, being number-conserving simply means that the number of ones is constant during the whole evolution of the system. Yes? And this is known that among all elementary cellular automata, there are only 5 that are number conserving. And here we have identity, shift to the left, shift to the right, traffic to the right, and traffic to the left. Maybe to describe the dynamics of these cellular automata, I will use particle representation, which means that the state 1 is represented by particle, and the state 0 represents an empty cell. So, for example, here we have identity, and particles don't move at all. Yes, it's very simple. Here we have shift to the right, and the pattern of particles does not change, and the particles simply move to the right. Yes? So this is, of course, number conserving. And here we have traffic to the right, and this is more complicated because each particle seems to be turned to the right, and it is moving to the right only if there is an empty space in front of it. Yes? So, but only these ones we have. However, one can consider some finite grids. Finite grids, not the whole infinite grid, but finite grid. And then we have the first and the last cell, and we have to choose some boundary conditions. Yes, and here we see periodic boundary conditions. So we think that the last cell is glued to the first one. So the cells are arranged along a circle, yes. But here we have null boundary conditions, which means that outside of the grid we have some kind of dead zone. we have here permanent 0, here and here. And okay, so we have new grids, finite grids. And maybe some elementary cellular automata are also number preserving on these finite grids. And we see the results, it's very old and new results, that for this case, with periodic boundary conditions, we have still the same 5 number preserving elementary cellular automata. And here, when we want to have null boundary conditions, we left only with this one with identity. And okay, so this is very important. Let us imagine the following scenario. There is some new researchers, very young researchers, and he wants to find all number conserving elementary cellular automata, but using a computer only. Yes? He does not know the main result, yes, but he has a computer, or she has a computer, and he wants to find all of them. And if he starts with computer experiments on very short grids, for example, 5-cell grid, 6-cell grid, and the experiments find that there are only these one which are number conserving on this short grid. And then 6-cell grid, and he get also the same one, and 7-cell grid, and so on. How long? Yes, it depends on the computer capabilities. Yes, and he may suspect that this is a good answer also for the infinite grid. Yes, and he will have no proof, but we know that he will be right. Yes. And yes, when we start our adventure with non-uniform elementary cellular automata, we hope that we can do this the same way. First, to consider finite grids and find all number conserving non-uniform elementary cellular automata on these finite grids, yes, and think not too much, a little, and to discover all, yes, for the infinite grid. Yes, but we see, okay. So, the definition of non-uniform elementary cellular automata is very simple. Yes, we give freedom to the cells. Yes, so we have our main grid Z. Yes, the infinite grid. And we also consider some one-piece subgrids of this whole grid. Yes, so here we have subgrid with left tie, with right tie, and of course finite grids. And these finite grids only are perfect for computer experiments. Yes. And when we have some grid G, and G is any of them, yeah, then we can choose any sequence of Wolfram rules, and then we have defined non-uniform elementary cellular automata by this formula. So we see that each cell can use its own Wolfram rule. Yes? So, each own. Maybe it is the same, maybe not. It's not important. Yes? And of course, here we have the last cell. Here we have the first cell. So, we need some boundary conditions. And here, of course. And in these cases,
we consider only null boundary conditions because periodic one has no sense. But here we will use both null as periodic boundary conditions as well. Okay. So of course, when we have some sequence of local rules, yes, that choosing some boundary conditions may the behavior of the cellular automaton may depend on our choosing of boundary conditions. So we will distinguish between these cases with this smaller lower index. Yes, here we have periodic boundary conditions, and here null boundary conditions. As we see, yes, for this rule sequence, this automaton is number conserving with periodic boundary conditions, while with null it's not. Okay. Yeah, and here we see our examples concerning finite grids. These results are published, yes, and some examples, very simple, we see here. So this is the simplest one, identity on a grid of length 1, only one cell, and we put to the cell identity. So it is of course number conserving, yes. And then we have S, it is automaton on very short grid of length 2, yes, and we see the action of this cellular automaton here by putting the outputs for all possible initial configuration. So because the grid is very short, so we have only 4 possibilities. And yes, as we see, in each time step, the particle from the left cell goes to the right, if there is any, yes, and from the left goes, from the right goes to the left, yes, and it is also this cellular automaton is periodic with period 2, yes, and it is of course number conserving. The next, we have a family of cellular automaton labeled by K, yes. So we see here one of them, and for some sample, one sample initial configuration. And yes, we have here these K plus 1 cells act as a traffic to the right, and the last cell stops this traffic. As a result, we see that all particles are lining up one after another at the end of the grid, and then particle stop moving. So this cellular automaton for any K is eventually constant. Yeah. Okay. BK is just a reflection, mirror reflection of AK. And now, okay, when we have these examples, we may think about them like Lego bricks and use concatenation to get some more complicated examples. Yes, to glue these guys, and yes, to create new examples. But this is all. This is all. Yes, we have a theorem. We prove the theorem that there are no other number conserving non-uniform cellular automata on finite grids with null boundary conditions. Yeah, so all of them are very simple. Yes, and what when we consider periodic boundary conditions? And it is strange, but it is the same, almost the same, yes, because yes, we have the result here, it's proved, of course, that we have the classical ones, yes, the classical ones, shifts and traffics to the left, to the right, and any other is like that there is some special place in the grid, yes, some kind of barrier. Then when we cut in this place, we get a cellular automaton with null boundary conditions, which is a concatenation of A, B, S, and identity. So in our opinion, these ones with null boundary conditions are can be treated as good blocks for building some examples. Yes, but because this is enough, only these classical ones are added here. Okay, so some exercise for us. Yes, so now we are in this point that we have full information about finite grids. Yes, and we see that regardless of the length of the grid, yes, small or very, very long, yes, we have all number conserving non-uniform cellular automata on these finite grids are built from these blocks, regardless of the length of the grid. So maybe we guess how the non-uniform, number conserving non-uniform on the infinite grid look like. Maybe we guess. So of course, we can use these Lego bricks to build, yes, some examples. Yes, because we can use concatenations, infinite, yes, to the left and to the right, and okay, so we have some examples. Moreover, we can modify this one, AK, by increasing k to the infinity and put it here to the left. So we have this one and traffic here, or to other side by increasing k here. So we have the first cell and then traffic. Yes, so we can modify AK to such blocks. Of course, we can increase k to the left and to the right both, but then we have the classical traffic, yes? So this is not interesting for us. The same for bk. And yeah, so we have 4 new blocks, We can add this to our Lego, yes, and to build new examples, yes? Okay, so computer help us to give these examples. And is this all? Yes. These counter examples say no. The world of number conserving non-uniform elementary cellular automata on the infinite grid is much more surprising. Yes. Let's take a look at the first counterexample. What we see here. We have the first cell, yes? So this is a subgrid of the infinite grid, yes? And we put the Wolfram rule 0 here, and then shift to the right. So this this cellular automaton is of course number conserving because particles simply move to the right. Yes, we have start line here, yes, and yeah. Okay, but it is very strange for us because 0, this local rule, is not double legal. What this means? Local rule is legal when 0, 0, 0 leads to 0 and is double legal when also 1, 1, 1 leads to 1. Yes? And it's very strange because we are used to this. Then every elementary cellular automaton, if it is number conserving, it has to be double legal. And when we consider non-uniform elementary cellular automaton, then the first lemma, the first technical lemma we use is when some local rule co-build such cellular automaton, it has to be double legal. But we see this is not longer true for the infinite grid. Yes. And the second counterexample. We see here the conjugation of the first. The conjugation. Yes. And this cellular automaton, of course, is not number conserving. It is again strange because we are used to this, that conjugation preserves number conservation. Always. But it is not longer true for the infinite grid. Yeah. So we, yes? Okay. So we need some theoretical tool to solve this problem. Yes, to find all number conserving non-uniform elementary cellular automata on the infinite grid. And we decided to use a very simple mathematical tool, very simple polynomials associated with local rules. This approach has already been used, for example, to study fuzzy cellular automata, yes, but in that case, the polynomials were derived by fuzzifying the disjunctive normal form of a given Boolean local rule. Yes, we have simplified this approach by using functions that are affine in every variable to induce the same effect. Yes, and we use this tool several times successfully, but we, in our study of continuous cellular automata, because polynomials are very good for this, for definition and so on, and it appeared that this tool is also very good for discrete cellular automata. Yes, so good for us. Okay, so here we have a polynomial associated with a given Wolfram rule. Yes, and additionally, we need some polynomials called left, central, and right. Yes, and if we define them like here by these formulas, then we can prove the following theorem, which is, as you see, necessary and sufficient condition for rule sequence to be number conserving non-uniform elementary cellular automata. And this is in a language of polynomials. So this is very, very easy for us. And for example, for this theorem, it is not very hard to list all elementary cellular automata that can co-build such a sequence of rules. And there are only 16 of them. yes, these are not double legal, for example. And we see them all here with the left, central, right polynomials, yes. And what is important, when we have 0 in this column, for example here, this means that this Wolfram rule is independent of the last variable. And when we see 0 here, it means, in particular, that this Wolfram rule is independent of the first variable. It turns out that the places in the grid, in the infinite grid, where some local rule, which is independent of the last variable, meets a local rule, which is independent of the first variable, are crucial for our consideration, are crucial. And we will call these places like barriers. So we see here, yes, if some automaton has a barrier at M, yes, maybe there is no barrier in this automaton, but by this sign we can yes, here we have all barriers for this automaton. And so, okay, and several technical lemmas and several theorems later, we have main results, and the first one is here. Yes, there are only eight number-conserving non-uniform elementary cellular automata on the infinite grid without barriers. Only 8. And here we have 4, the classical ones, shifts and traffics. And here we have some new ones. And to see their dynamics, we have to use this red push button. Yes, okay. I don't know if I can do this. Yes, this, okay. Yes, it is a website of Maciej Dziemiańczuk. Yes, and we see here, yeah. Okay. Yes, the dynamics is here. I can change, for example, this one to 0. Yes, and so on. Or maybe more ones is better. Yeah. Yes. Generally speaking, yes, all particles goes to the left, but here, according to the traffic, and here, according to the shift. And this one cell region yes, allow particles to change traffic to the shift. But all particles go to the left. Okay, and the next one, yes. Yeah. So we see the dynamics, yes. And okay, maybe 0 here. Yeah. Oh, this is important part. Maybe 1 here. Okay. So, and here, generally speaking, all particles goes to the left, and on the right side of the grid, like traffic, and on the left, like shift, but there is some difference because we have some region here, yes, consisting of two cells that preserve these particles to go here. Yes, so this is quite different from the first one. And it's all because, well, I'm here. Yes, because this one is a mirror reflection of this one, and this one is a mirror reflection of this one. And there is no others without barriers. And when there are some barriers, and the result is here. The result is here. When such number conserving cellular automaton has at least one barrier, then it has to be built from these Lego bricks. Yes, and do you remember that computer simulations give only these guys? This one and this one. But we have new here and here. Yes? Yes, and this is unexpected. Okay, so last time I presented these 3 questions, and as you see, the results I just shown answered the first question. Yes. And this moment, we have no so good mathematical tool to consider cellular automata whose state set has more than 2 elements. So this question is still open. Yes. As for the last question, we believe that our tool we use here, meaning polynomials, is also good for this case, at least for radius 1.5. Yes, so cross your fingers. We can do this. Yeah, thank you very much.
Thank you, Barbara. I have a lot of questions, but first I would like to ask if some of you has comment or questions. Okay.
Yeah.
So can someone help me with the microphone? Oh.
Did you find some rules where the particles move left and right at the same time, or where the particles are bounced back from the borders? It would be interesting to see such rules.
Yeah. Yes, I can. Yes, you can glue some blocks from this, and for example, this one. We discussed this one, 0 and shift to the right. Yes, and when you use this one and only this one, yes, and concatenation of these 2 guys, yes, you have some number cancelling non-uniform, yes, then half of particles goes to the left and half to the right. Yeah.
Thank you.
Thanks. Anybody? Okay, I have a question. I realized that just when you showed the polynomial slide that actually these are essentially the Boolean derivatives with respect to the left to the right. I don't know if you are familiar with this. We can discuss. I wrote some paper about them. So you can introduce a kind of derivative. I mean, if you change one bit, how this changes, no? And so exactly these two. And so essentially, if I'm right, if you define the Jacobian, I mean the derivative of each side with respect to the side, to every side of the other. Clearly here it is 3 diagonal, since you can only have, actually you have number conserving if each row of your Jacobian has just one.
Yeah, yes, yes, but okay, but yeah, but the difference is here when we have derivatives, but for different local rules here. It's not for the same local rules, so this is
Perfect.
more
Okay, but
complicated.
we shall discuss this.
Yeah.
And now, if you go back one slide,
Yeah, okay,
if I'm
yes.
right. Actually, this counterexample works only for semi-infinite lattices.
Yes, but when we can use concatenation, oh yeah, concatenation, and to glue here, for example, identity.
Yes.
Yes. So this is for the whole infinite grid. Yes, but this is the region we are interested in. Yes. Yes.
Okay, thank you. So, if there are no other questions, we
Coffee
can
break.
have our coffee break. And so just say last. So we meet all together here so that you can write down your name if you have not done yet on the blackboard, just for taking a photo of the participants of today. And I can give you some, say, direction on how to orient yourself here and other technical details. So please, thanks all the speakers of this first session. And